Today, we're diving headfirst into one of the biggest, thorniest problems in quantum computing. And we're not just going to talk about it, we're going to show you step by step how to actually solve it with code.
So let's start with a pretty surprising fact. Quantum computers are, well, kind of messy. They're inherently noisy. Their most basic components, these things called qubits, are incredibly fragile. Unlike the super reliable bits in your laptop, qubits can be knocked around by the tiniest environmental disturbance, which can totally flip their values and corrupt your whole calculation.
And this fragility leads to all sorts of different errors. You've got your bit flip, which, yeah, is exactly what it sounds like. A 0 becomes a 1. But you also get these sneakier errors like phase shifts or even the qubit just losing its energy completely. Any single one of these can wreck our results unless we have a solid strategy to fight back. So here's the journey we're taking today. We'll kick things off by really understanding the problem. Then we'll introduce our toolkit, and from there, we're getting our hands dirty. We are going to code a circuit, watch it fail because of noise, and then, right after, write the code that actually fixes it. This is the real path to building fault-tolerant quantum computers.
Okay, so let's meet our architect's toolkit for this job. It's NVIDIA's CudaQ. Now, this is an open source platform, and it's built specifically for hybrid quantum classical programs, which, as you're about to see, is exactly what we need to wrestle with error correction. The absolute core concept you gotta know in CudaQ is the kernel. You can just think of it as the blueprint for your quantum circuit. It's where you lay out every single quantum operation. So let's go ahead and build our first one right now.
All right, time to write some code. First mission, we're going to build a super simple quantum circuit, and then we're going to break it on purpose. This is going to let us see this whole noise problem up close and personal.
First things first, we define our kernel in Python. Okay, so we start by importing the CudaQ library. Simple enough. Then you see this little @cudaq.kernel thing? That's called a decorator. And it's basically a flag that tells CudaQ, hey, treat this function as a quantum program. Inside, we just allocate a set of 3 qubits using CudaQ.QVector3. And just like that, our quantum hardware is basically initialized. And by default, they all start in the all 0 state. Okay, next up, we're going to create a noise model. See, we're not trying to run some perfect, idealized simulation. We want to simulate a real imperfect quantum computer by introducing one of the most common errors out there, a bit flip. Now here's how we can simulate that hardware flaw. We make a noise model. Then we define a bit flip channel and give it a probability of 0.10, which just means there's a 10% chance of an error. Now, the really crucial part is that we tell the model to apply this noise only to the X gate and only when it's acting on our first qubit, qubit 0. This lets us simulate a really specific, targeted imperfection. So in a perfect world, our simple kernel doesn't do much at all. It just sets up 3 qubits, which all start at 0. So if we measure them, we should get 0, 0, 0. Every single time. A nice, clean, predictable outcome. But now for the fun part. Let's run that exact same circuit, but this time with our noise model switched on. We use the CudaSample function here, which is like running the experiment over and over on a real quantum computer and just collecting all the results. And there it is. This just perfectly illustrates the problem. Instead of that clean, 000 state we expected, the noise corrupted it into 100. Our first qubit flipped. Our calculation is officially wrong. Now imagine this in a huge, complex algorithm. A single error like this could throw the entire thing off. So how do we even detect that an error happened? And here's the real catch. We can't just, look at the data qubits. The very act of measuring them to check would instantly destroy their delicate quantum state. We need a much more clever way in. And that clever way in is a concept called a syndrome. Think of it as a pattern we get from measuring some extra check qubits, which are often called ancilla qubits. It's a kind of indirect measurement that acts like a signature for a specific error. It tells us what went wrong without ever revealing the precious data itself. And this whole workflow is really the heart and soul of quantum error correction. First, we encode our data across multiple physical qubits. Then we run this continuous loop. We use those ancilla qubits to check for errors, we measure them to get the syndrome, then we use a classical computer to figure out the error, and boom, we apply quantum gate to correct it. So let's see how all that logic actually translates into code. We are going to build a new CudaQ kernel that can detect and correct the exact bit flip error we created just a minute ago. So how do we actually get the syndrome? We use a gate called a controlled NOT, or CNOT. You can think of it as a little logic check. It connects two of our data qubits to a third ancilla qubit and basically asks, hey, are you two data qubits consistent? It records the answer by flipping the ancilla from 0 to 1 if they're different. And here is the absolutely crucial part. We only perform a measurement that's MZ in the code on the ancilla qubit. If the data qubits are fine, the ancilla measures 0. If they're different, which signals an error, the ancilla measures 1. This gives us our error signature, the syndrome, without ever collapsing the quantum state of our actual data. It's brilliant. Now for the classical part. Based on the syndrome value we just got, we can use simple conditional logic to decide what to do next. And this right here is the magic of the hybrid model. It's just a simple if statement, running on a classical processor that's controlling the quantum recovery operation. If the syndrome tells us there's an error, we just tell the quantum machine to apply a corrective X gate to flip the qubit right back where it belongs. And now for the moment of truth. When we run our simulation again with the exact same 10% noise model, but now with our correction code active, we get the right answer. The error still happens, but our code catches it and fixes it in real time. We've just successfully debugged the quantum realm. So what does all this mean for the future? I mean, this was a simple example, but it's way more than just a programming exercise. It's really a window into the future of compute. This simple detect and correct loop that we just built is the fundamental building block for what we call fault-tolerant quantum computers. By scaling up these exact techniques, we can create what are called logical qubits that are effectively immune to noise, paving the way for machines that can solve problems that are completely beyond our reach today. By mastering these techniques right now, with platforms like CudaQ, researchers are actively building the foundation for the quantum discoveries of tomorrow. The question is really starting to shift from if we can build a reliable quantum computer to what profound challenges we're going to solve with it first. Thanks for watching.